Welcome friends, in today's lecture of machine design we are going to discuss different loading conditions and design under different loading conditions like static loading and dynamic loading. After that we will also start the discussion about the failure theories and we will complete different theories in forthcoming lectures. Let us start with design for static loading. You know that when there is a normal stresses, simple stresses applied on a machine element, then you know that how it will fail. By using the universal testing machine we can find the induced stresses, and by comparing with the SYT, that is the yield strength of a material for ductile material, we will compare it with the induced stresses and we will find or establish a relation between the SYT and this sigma stress inside the material, so that we can find the relation and which will be helpful for designing the material machine components under simple loading condition. Let us say uniaxial loading condition shown here in this specimen which we use in universal testing machine. We have generally studied two type of loading condition for static loads, that is first one is simple loading condition and another is complex loading condition. This first type of loading condition we will call it as a simple loading condition. Here you can see that there is only a one uniaxial forces are applied on the specimen. If there would be a different type of forces, like let us say in the same axis, if there is a shear force which causes shear stress or shear strain along with the normal stress in the longitudinal direction, both are acting simultaneously, then we will call it as a complex loading condition. Here in the next slide I will explain. Before that we will study the design procedure for simple loading condition and how we will design a diameter or a dimension of a machine component which are under simple loading condition. This is another example of simple loading condition. Here you can see even though there are stresses in let us say this direction and as well as in this direction, if we consider this as a y direction and this as a x direction, then here is strain and as well as stresses induced in x and y both directions, even though this will be called as a simple loading condition. You know that if we will compare maximum shear stress with the SYS, that is yield shear stress or yielding shear stress, that is the yield strength of the yield shear strength of the material which we are considering, we can find the dimensions for the assumed or required machine element, for the required machine element. Here I will discuss a complex loading condition. Before that I will solve a one example for simple loading condition. Here you can see there is a circular shaft, cylindrical shaft having a circular diameter and 5 kilonewton tensile force is applied in the longitudinal direction, and what is given, it is given that MS shaft is there, that means mild steel material is used for this shaft, and its strength, that is yield tensile strength, is 150 megapascal. Now we have to find the safe diameter, that means at which diameter this will sustain this much applied forces. In the solution we will see the first we will derive a relation. Just a minute, let me change the color of the pen. From here we will start our solution. Just a minute. What happened? Okay. Yeah, now here I will write solution. This was the given information, this much. Now we will write a relation between strength of the material used, that is material mild steel, and the induced stress, that is sigma. So we know that if it is a mild steel, that means a ductile material, so we will compare it with the SYT, that is yield strength, not with the SUT, which will be useful in the brittle materials. Here, as our material is mild steel, that is ductile, so we will use this relation for finding the diameter or for designing this machine component. We will compare these stresses induced with the SYT divided by FOS. That means the factor of safety is 2. If there would be a factor of safety of 1, let us say, here I can explain you, then we will just our strength will be very close to the SYT or SUT. Here you can say, if I will put here one value, then you will find sigma max, that is induced maximum stress, will be nearly equal to the SYT. But generally we take FOS, that is factor of safety, more than 1, let us say 1.5 or 2. Now I will solve this equation and will find the diameter. You know that stress is nothing but the force upon area, so in the place of stress we will find F by A, put F by A, and here we will put the values given, that is SYT is given 150 megapascal. Here once we put these values, we know that sigma is equal to SYT by FOS, and force is nothing but stress is nothing but F by A, or you can even write like this, as we have written our relation in terms of FOS, right? Now if I will write SYT by FOS in the left side, it is again same, F by A, right? SYT by FOS. Is this similar to this one, right? So by putting the values, force is 5 kilonewton, diameter area will be the cross sectional area of the cylindrical shaft, and you know that the cross section will be a circular, that's why the area of a circle pi d square by 4, and by putting this value we will get the diameter approximately equal to the 9.21 mm. Here you can find that under complex loading, component of same dimensions and material may fail at very less induced stresses, that is normal or shear stress, as compared to its strength. But in case of simple loading condition, what is happening, we are getting as good as if we consider FOS equal to 1, we will get this induced stress, maximum induced stress value nearly equal to SYT. So that is the basic difference in complex loading and simple loading. Here you can find what is the difference between complex and simple simple loading condition. Here you can find here are both the normal stresses as well as shear stresses are present in this machine component, or the smallest part of the machine component. For simplicity, let us say this component is like this, a circular shaft, and both the torque and normal stresses are acting. Let us say this is the torque acting in this direction T, this is any force F, right, and this will be a counterbalancing torque. This is the same force F, like this. Now if we will take any small component from this cylindrical shaft, you will find such a similar condition where there are shear stresses as well as normal stresses will be acting on the smallest component. Then by integrating this small area to get the forces or stresses all over the cylindrical shaft, we will get the value by integration. Here we just have to find what is the difference in complex loading condition and simple loading condition. So here you can see that complex loading condition includes loading in different planes causing shear stress along with the either uniaxial or biaxial or triaxial loading. You know that here in y-axis also there are forces and stresses, and in x-axis also there are stresses. So that means loading is also in x and y direction also. So that's why this type of loading is considered as a complex loading condition. And for this we cannot use simple like this equation SYT or SU2, because we don't know whether it will fail under the shear or under the normal stresses, that due to shear stress or normal stress. So for this we require different theories of failure, right? These are the two equations for this is for the brittle material, as we know, like let us say glass or anything, and this will be for the ductile material, right? But we cannot decide if there is a complex loading whether it will fail under shear or under the tensile stresses. So different failure theories are important, so we will discuss it. Just have we have to find the difference between the complex and simple loading condition. Component bears simple normal stress nearly equal to the strength of particular material. Here you can see if FOS is 1. In case of ductile material and ultimate, that means yield stress, we will use yield strength for the ductile material and ultimate strength for brittle materials if FOS is 1. And in case of what we have seen complex loading, we will get a very less strength if there is a complex loading. Here we have stated it. Under complex loading, component of same dimensions and same material may fail at very less induced stresses, whether it may be a shear or normal stress, as compared to the its strength in the normal stresses, or the if whatever the strength we have find out from the universal testing machine. It will fail before that because there is a complex loading condition. We have discussed first example in case of only normal stresses. Now we will find the complex loading condition. Here you can see that there are two types of forces acting, or two types of stresses will be generated. So this is a complex loading condition, and here we will get the shear stress as well as normal stress. We have found this from the torsion equation, right? We will get the shear stresses induced is equal to 16T by pi dq, and normal stress will be force P upon A, cross sectional area A. Now here we will find the significance of failure theories. To find the failure mode in complex loading, we need different failure theories. So What will be these different failure theories? There are actually 5 different failure theories, like maximum normal stress theories, maximum normal strain theory, then there are different like maximum distortion energy theory and maximum shear energy theory, like that. One by one we will discuss in coming classes. Before that we will discuss what is dynamic loading condition. We have seen the static loading condition. In that there were two loading condition. First was simple static loading condition and second was the complex static loading condition. Now we will start dynamic loading and we'll discuss further in detail in further classes what will be the dynamic loading condition, how will be the design for the dynamic loading condition. First define and let us understand what exactly mean the dynamic loading condition. If there is a change in the point of application of a load, this is the first requirement, so that we can call the load as a dynamic. Here you can see the first point. If there is a change in the point of application of load, then we will call it as a dynamic loading. Similarly, if there is a change in the direction of load, let us say sometime it is applying in the compressive manner and another time it will acting is a tensile manner. That means tensile and tension and compression, this is repeated type of loading is there, then we will also call it as a dynamic loading. And third case is that if there is a change in the magnitude of the load, let us say at one time there is 10 kilonewton, at another time there is a 5 kilonewton force is acting. Like this, if it is changing, whether it can be a fluctuating or completely reversed or any type of load, and such type of loading is can be seen in the gears. If you consider a gear or shaft, you may find that, let us say this is a gear having teeth. If it is engaged somewhere here, then what will happen with another gear? Here will be some compression will be experienced. Let us say this is the complete shaft. This is the complete shaft. At this point it will experience compression, and at this point there will be tension. Once the gear rotate in this direction, let us say it is rotating, and this portion will come at this portion, then this portion when will be in engaged condition with another teeth, then this shaft will experience compression instead of tension. Like this, the shaft is under repeated, or what can I say, reversed loading. At every rotation there is a change in the direction of loading. That's the point. And in under dynamic loading condition, component of the same dimensions and material fail at very less induced stresses as compared to its strength in static loading. Example is the fatigue. If there is a compression and tension repeatedly applied on a component, let us say it is a wire, if we will do like this, first we will deform it like this, then secondly like this. If we will repeat it continuously, you will find very less time and less forces it will fail. Otherwise, if you will apply force in this direction on this wire, it will require very large amount of force to fail this wire, right? That's the main difference in dynamic and static loading. And how we will say that the component has failed? If it is undergoing a permanent deformation or YT, we don't compare induced stresses with elastic stresses in the elastic limit. We either compare it with SYT, this is the stress strain curve, right? Either SYT or let us say SUT. The reason behind why we compare with only these values, because here itself the plastic deformation starts. We have studied in the strength of material. If you have not studied the or watched the some lectures, you can see our previous lectures and get the clarity about this stress strain curve. So in this elastic limit from this to this area, there is a very negligible deformation which is acceptable. That means under that deformation, component will perform its function with a, let us say, acceptable value in change in the dimension. So there will be no what I can say lesser efficiency, or there will be a permissible change in the dimension. So we can assume that this is a safe stress, or the safe zone where we can apply forces up to this limit. After this there will be a plastic deformation. Let us say it is a machine component and we are applying force greater than SYT. That means if its length is increased to this much length, the previous was only this much, and the latter, after applying load, this much elongation has occurred. So you will find that either the machine component is not fitting properly and it will not perform, or it will not give expected performance. So this is, we call it as this component has been failed. No need to actual fracture or crushing or the exact what I can say failure which we can see by our eyes. Even though there is a plastic deformation at stresses greater than SY2, then also we will call that the machine component has failed. It is not performing as per its required performance values or the limits. That is all about the design under static loading. And if I would like to give some examples of dynamic loading, it can be either a completely reverse loading like this. Let us say I will draw a figure here, completely reverse, like let us say this is a 5 kilonewton, this is a 10 kilonewton, and this is, let us say, 0. If I will draw a completely reverse, let us say like this type of loading condition will be first 10, then let us say this is somewhat 3 at 3 kilonewton, then again it will become 10, again it will become 3, like this, completely reverse. Direction is completely reverse. And repeated loading will be like this. First it will be positive value and then become 0, then again positive value, then again become 0, like this. Let us say it is somewhat 5 and here it is 0. In case of brake, the example for this repeated loading, when we apply brake, then only there is a loading on the brakes or the brake plates. That loading will be called as a repeated loading. And fluctuating load is the another type of example. Here this load can be called as a fluctuating, rather completely reverse. In completely reverse, I will draw another figure for it here. Completely reverse, when we can call it completely reverse, when there will be a change in the magnitude, let us say Here we should call it actually fluctuating, not the completely reverse. And completely reverse will be like this: from 0 to positive value, then negative value, positive value, then negative value, whatever it may be. Let us see, this is tensile loading 5 kilonewton, and this is the 5 kilonewton compressive, like this will be called as the completely reverse loading. If we will plot a graph between the load force and the t time t, okay, that's was all about the loading conditions and the design of the machine element under static loading. We will extend this discussion about the dynamic loading and the theories of failure in coming lectures. We will discuss different theories of failure and the criteria for static loading, whether it is following in case of brittle material, which theory is suitable for brittle material, or which theory is suitable for ductile material, whether maximum normal stress is suitable or maximum normal strain theory is suitable. We will see in next lecture. Till then, you can see or study our previous lectures on the strength of material, because it is very important to understand what is SYT, SUT, then the stress strain curve which I have drawn here. It is very useful for the design of the machine element. In strength of material, we have not considered the dynamic loading, just we consider there is a, let us say, static loading condition, and the complex structure of the design of machine elements we will discuss in machine design subject here in this series. This was the first lecture of the machine design. In coming lecture we will discuss the complex conditions, the dynamic loading, failure theories, and related topics to this machine design. Thank you for watching. So signing off for the day. Thank you once again.